Okay.
Hey, go ahead.
So we're Group 5. We are presenting the Formula Society of Automotive Engineers Car Radiators Design. My name is Brandon.
All right, I'm Jeffrey Draper.
My name is Dan Kitcher.
The project will be co-advised by Professor Moore and Professor Maya, and this presentation is today.
Right,
so the problem, oh yeah, go for it, Danny.
Oh, sorry. All right, for the problem definition, our project, we're trying to put an Apilla 550SX engine into the current chassis for the Formula SAE car, and what we're doing is we're working mostly in the cooling system. We got to design a radiator and all the piping and the reservoir to efficiently cool the engine. We have to manage it over different operating temperatures, and we also have to find the spot to securely mount it. And it has everything that we do has to abide by the rule book so that it can run in the regulation races.
All right, so our project has a couple of design constraints. It must be Formula SAE competition rulebook compliant. The coolant itself has to be 100% water, and there must be a catch can for any runoff fluid. And this radiator must fulfill some size constraints too. It cannot interfere with any other parts of the car. The cost is based on the club's budget, and we have to have this part ready for December 2020.
Yeah, and so the project duration is going to be both for the Senior Design 2 presentation as well as a handoff to the FSAE group so they are familiar with the system and can present on it at competition.
All right, as far as the users go, it is the club car, and so most of it's going to be managed by the students in the club. They're going to have to maintain the car and the cooling system. They have to be familiar with the operation, how everything works, the fluid being used, which is water in our case, because that's what the rule book states we have to use. And it's also going to be manufactured by us. We're part of the club, and so the entire chassis and everything is all about the members of the club. Also, as far as the design review goes, when the car is raced in competition, it's going to have to be presented to a board in charge of the operations before the races, and so they're going to have to, the members racing it are going to have to understand how the systems work and ensure that everything that we do complies with the rule book.
So for iterations, there's no exact iteration to be compared to the cooling system. However, the system is going to mount to the car chassis, which has been completed in the past. This has been designed and fabricated, exists in the labs. The suspension has already been designed, but it's not been constructed. Our radiator must mount to this and not interfere with any of those systems. We're assembling a CAD model of all these systems to ensure that that's the case. Positioning will also be controlled by sections of the rulebook. For future iterations where this project's going to go, the engine was supposed to be built in parallel with this project. Given the current situation, this will not be done. So test apparatus is going to be required, possibly running off a similar engine or in similar design constraints to make sure that the design functions and is compliant with the rulebook. For literature, we are heavily using the FSA rulebook. This is available right online as a PDF. It's updated periodically. We are going to verify our designs to the 2020 version 2.1. This will help us verify the designs are compliant. Will help us check any of the standard constraints or requirements that the car is going to have. And this is not a design-oriented handbook. This is more of a pass-fail, will this design function? So the second piece of literature that we've been reviewing is a parametric study from the Applied Thermal Engineering Journal. This generalizes radiator behavior into a design-based cause and effects analysis in experimental conditions. We'll be using this to make our efficient decisions when based on manufacturability and performance. And this can be used to predict or verify results in the long run. Team members, there's myself. I find my strengths are in communication, documentation of the subject, hands-on learning. So I work on a lot of my own cars, adapting to new situations, and structural analyses, which will be heavily featured in the Senior Design 2 aspect of this project. My weaknesses are definitely experience in manufacturing and coding as far as any of that goes. That's it for me.
All right, I'm Jeffrey Draper, and I would say that my strengths are programming, CAD, particularly Siemens NX, creativity and out-of-the-box thinking, attention to detail, and one of my stronger classes was machine design. And for weaknesses, I would say time management, organization. I do sometimes require quite a bit of time to understand a topic, but once I do understand it, I'm solid, and presenting.
As far as my strengths go, I really like machine design, fasteners especially we're talking about right now, which I think relates really well to how we're going to fasten the radiator into the car. Fluid mechanics, I really loved. I repair and work on a lot of my own cars, even the cooling systems, radiators. My own car, I had to fabricate my own radiator brackets to get into my car. I love hands-on building, working in the shop, 216, 217 kind of stuff, lathes, all that kind of stuff, putting things together. And I'm very meticulous, detail-oriented. I like things to be very precise, very clean, fitting. As far as my weaknesses go, I'm not very good at coding or programming. I'm also just not very good using computers as much as I am with my hands. Unfortunately, I haven't taken heat transfer yet, so I'd have to say that's one of my weaknesses. Sorry, Professor. Also, staying in budget. Sometimes once I start to get an idea on a project, I try to get it as good as I possibly can, so it's often hard for me to stay in a budget. And time management. Sometimes when I get on a roll with something, I just want to spend as much time as I can on it, and other times it's hard to fit it. So I would say those are my strengths and weaknesses.
So for our task list, we are currently in the research and planning phase. We are currently pursuing some general solutions, and we expect to start designing specific solutions within the next few weeks. And after that, we're going to have to build a prototype. We're going to have to actually test this. And we're going to have to design a test apparatus. And we're going to have to document everything so that the Formula SAE Club can have access to that information. And one of our preliminary ideas was this sketch for a radiator. It'd be a series of thin parallel pipes for the fluid flow, and the flow would ideally be turbulent to increase the heat transfer rate, and the large side pipes would actually connect both ends, and there'd be a fan added for forced convection. We'd probably use a high thermal conductivity metal, likely aluminum. The fins themselves would be thin, rectangular, and geometrically simple, based on the manufacturing equipment we'd have at the school. And the dimensions would be based on size constraints of the car. And I'm already anticipating that sealing junctions between the large pipes and the smaller ones might be difficult, as well as attaching the fins to those pipes and maintaining a high thermal conductivity. Perhaps a thermal paste would be an option.
Just to add to that too, we examined the radiators that were put in the bike that the engine was taken out of that's in the car, and although it's not exactly the same shape or aerodynamic structure, the radiator design is similar to what Jeff was just talking about. It doesn't have a fan, and so I think the added fan that we're going to have is going to provide a little bit of extra cooling, especially depending on how we're going to mount it compared to how the bike is. But as far as design goes, it's a very similar design to what Jeff was just talking about.
Task 4 that is currently in progress. This is determining numerical values for the requirements. Namely, this is going to be for size, shape, and location of the radiator, planning out where we're going to be able to fit it. We expect, well, this did take 2 days, which was longer than expected. The files I was able to get from the FSAE club are more disorganized than I thought. So we've been sorting file structures to build assemblies that function in SolidWorks. Once we have a SolidWorks model of the frame and where the tires will reach the ground. versus the dimensions of the tires, we're able to determine where the free space on the side of the frame will be, which is our target area for building the device. We have to consider both square and round tube is used on the frame. We want to verify these model dimensions. I've reached out to the FSA club to verify this is the correct model. This is the dimensions that were used to manufacture these components. Just to check all the boxes, make sure everything works. The next step for this task is to continue building assemblies, determining the depth constraints so we can extrude boundaries and have a complete boundary for where the radiator can be or can't be, and check this with the rule book. This is the result of the data. These are obviously exact measurements. These are going to be simplified so that we can use them, but these directly match up with the geometry and location of the frame. So this will be what we'll be using to determine mounting locations and what we can do as far as geometry. And finally, for the Gantt chart, so our primary concern moving forward is completing the tasks that we are in the center of. We've determined some numerical values, but we need to verify these and keep moving forward. We have a lot of parallel activity going on right now. So we have to work individually mostly to develop these systems probably to 70–80% before we can reconvene and put all the projects together. We're not far behind schedule, but we are behind schedule, just worth noting.
And in conclusion, we realize that the research and the planning phase is a little slower than anticipated. It takes a little bit of time to completely figure out what we're trying to do, especially get constraints from the team members about how to put the to get our actual dimensions in for where we mount the radiator. We also realize that, Professor, you were right, the Gantt chart is extremely important, and being able to follow it to make sure that we're on track and doing as much as we can to stay on track is important. And there's a lot of individual work that's required to keep us on track. We all have different strengths and weaknesses. And so some of us are a little bit better hands-on. Other people are a little bit better on the computers, designing software. And so there's a bit of work that each person can contribute to the formula card. But I think overall we're making pretty good progress. And I think that's going to be pretty successful by the time we're done.
And that is the end of the slideshow. Thank you for listening.